It used to be. Get a nice hyperbola equation when you do this. It was very exciting. So if we're relying on, let me get my highlighter out, this fact, this truth, unit circle related identities. All right, so circular trig, not hyperbolic trig. All right, and the reason I mention that is because there's a whole world of trig associated with the unit hyperbola, not the unit circle. All right, and so it opens up pathways hitherto unknown. Movie reference? Okay. Did you really just say hitherto unknown? Recent movie. Anyway, so if I'm going to make use of that piece of information, I might want to solve this for cosine theta and solve this one for sine theta. All right, so we'd be looking at cosine of theta is equal to x over 3. Sine of theta is equal to y over 4. All right. Looks good. Looks just like my screen. If I know that sine squared theta plus cosine squared theta is equal to 1, and I know sine of theta is the same as y over 4, I could do y over 4 as a quantity squared. If I know that cosine of theta is the same as x over 3, I could say x over 3 as a quantity squared. And this is a pre-calc strikes again situation. I'll clean it up and get it into its standard form. If you square each part and then actually swap the x's and y's, you get x squared over 9 plus y squared over 16 equals 1. Anybody know what that's the standard form equation of? An ellipse. All right, so we have a hyperbolic, see, that's how much I want to teach you. We have a parametric relationship that seems not too different from what we did on the previous page, but just based on the coefficients here, we could see that we're, yeah. I was going to say, can you just look at the coefficients of cosine and sine, you can see if this is different. Exactamundo, exactly. So yeah, once you make that recognition, you already know, all right? And so then it begs the question, all right, well, what if the coefficient of the theta is not equal to 1? All right, so we could do the same thing. Sine squared, I write sine squared theta plus cosine squared theta equals 1 because that's what people tend to recognize, that's unit circle related. But it's really sine squared of anything plus cosine squared of anything is equal to 1. All right, so, and the anything in this case would be the 2 theta. I'm about to write cosine again for some reason. All right, so this also has to be true. So if that's the case, and you can test it out. Put in anything you want for theta, anything that's real, and see what happens. Anyway, if you do that, we would be looking at x squared plus y squared equals 1. All right? And actually, if you think about that really carefully, it should make all the sense in the world. Right? Because the coefficient of your angle, your argument within a sine or cosine, whatever trig function, that coefficient always represents the what? If I had sine of 2x versus sine of x versus sine of half x. Close. It's something that we use to find the period. Close. It's one of the other words associated with it. So on the radio, there's amplitude modulation, and then there's frequency. All right, so we're looking at the frequency of the cosine wave. It's just basically saying that you're getting more cosine waves in a shorter period, right? Or in the same period, actually. So all this is telling me is that I'm just going to go around my unit circle more than once. But it's the same unit circle. Right? So then we get to this bad boy here. And if you follow what we did in example 6, you can see it's really no different. Because you could actually just jump right from here to the final answer, because what happened, we had the x. Once we divided that by the coefficient of the cosine function, that squared gave us the first part of our ellipse model. So same idea here. It would be x over a squared. And it would be the same idea for the y's, y over b squared. Equals 1. So that gives us the general form, the standard form, sorry, of any ellipse centered at 0. All right, so this is any ellipse centered at 0. For now, I'll call it 0, 0, but later on in the course, you'll see that we're just going to refer to it as 0. The reason being is once you start adding dimensions, I tell you we're working in the 16th dimension. To write 0, comma 0, comma 0, comma 0, comma 0, that sucks.
What's the number?
Oval.
Oh.
All right. So in terms of change from center, this one would be restricted based on whatever the A and B values are. And so in this case, we're dealing with particular A and B values of 3 and 4. All right, so that's telling us how far out we're going from center. And, you know, I'll give you the smallest, quickest of crash courses on this. You have center value, and it's x squared and y squared. Just like a circle, if it's x squared plus y squared equals something squared, it's centered at 0, 0 because there's nothing impacting the x and the y. If it was like x minus 2 squared plus y minus 7 squared, then you'd have a different center. Not the case here. Okay? But what this is telling us is that we have to go out 3 units left and right and up and down 4 units. All right, so 3 units left and right. I'm going to go purple for that. And then green for the up and down. 1, 2, 3, 4. And those values correspond with whatever you had to square in order to get your denominators. All right, so really, I mean, if you're already presented with the standard form, you would just take the square root of the x denominator. That gives us our horizontal movement, left and right, horizontal change. And the square root of the y denominator would give us our vertical change. So I can't draw, so you have to just pretend that that looks like a great depiction of an ellipse. I mean, just look at that beauty. All right. I think this would be a great time to bring back. Honestly, I don't think I would be able to teach this course like 10 years ago even, because my drawings are so terrible.
How do you get access to GeoGebra?
GeoGebra?
Yeah.
Just type in geogebra.org. Yeah, no, seriously, it's free. It's completely free until they decide it's not. Because, you know, like a lot of these web-based things, they're like, yeah, we have this free thing for everybody because learning, you know, society, it's great. And then they realize, oh, this is not sustainable. We can't afford to do this anymore. For a small donation, you know, and then after that, it's like, all right, it's going to cost you $5.99 a month. But at least for now, it's completely free. So geogebra.org, create an account with Google, because why not, right? Everybody has Google, yeah. So just do that, and then you could be doing what I'm doing in class. They have apps for the phone. The one thing I think, I mean, I haven't checked recently, but the 3D graphing, if they have an app for it, it's either escaped my attention or it just doesn't work. Right? but I have successfully used the 3D graphing feature of the website on my phone. So if you just go to the actual website, geogebra.org/3D, it'll bring up the interface, and it's easy enough to use. I mean, as easy as everything else is to use on a smartphone, which is to say that it's not always that easy. But yeah, look, good news. Yeah, we don't have to worry about what this Kosh and cinch business means. I really want to teach you about it. Can't. It's like a whole unit in and of itself. Converting rectangular equation to parametric equation. This is going to seem like the flimsiest thing in the world, because I'm giving you here a relationship, t equals x over 2, and so on, and then we're gonna basically decompose this into x and y equations. So then the question would become, all right, well, how'd you decide on these relationships? And my answer to that is I just made it up. Okay, so how would one decide on these relationships? The answer is you just make it up. If you have a choice in the matter, you just decide, all right, I'm going to let t equal x. I'm going to let t equal 20x. But generally, it comes from some sort of research. Like, you have to come up with a relationship that exists, but not arbitrarily, just through data collection and analysis. That's the important piece. All right, so anyway, what I want to do is substitute, because that seems to be the general theme here. We have y equals x squared plus 2x. And I'm saying that x is equal to t, so that means every x can go away and be replaced with a t. That was nice. Nice. Yeah, our final answer would be x equals t, but I'm going to write it as x of t equals t. That's coming from this guy. And then y of t would be equal to t squared plus 2t. All right, so what that allows us to do is introduce a time component. All right, but the time component here is it's flimsy, because it's basically saying that every step, every unit in the horizontal direction is equivalent to 1 unit of time. Is that always going to be true? I don't know. I don't think so. So we move on to the next one, where t is equal to x over 2. All right? If that's the case, then we would know just through cross multiplication that x is equal to 2t. And we would do our substitutions from there. We'd be looking at y equals 2t squared plus 2 times 2t. Clean it up. 4t squared plus 4t. And so our final equations, again, you don't get one without the other. X of t is equal to 2t. Y of t, stay with red, I guess, is equal to 4t squared plus 4t. All right, the interpretation. T equals x over 2 is telling us that time is moving at half whatever the units are for horizontal distance. All right, so for every 1 foot horizontally, that we're counting that as half a second, basically. All right, so it's establishing a framework for the rate of change. And so here it's saying time is outpacing the horizontal distance by 1 second, so it's the same idea. All right, so replace. Once you do your quick calculation, you get x equals t minus 1. Replace the x with that. You know, if it gets too cumbersome, then you would say, I mean, considering all we have to do is get parametric equations, so we're parameterizing this. If it gets too cumbersome, then just don't simplify it. Right? Not very frequently going to ask you to simplify stuff. So, I mean, there's some go-getters among us. Like, I'm gonna simplify this whether he tells me to or not, and then you do. Then you screw something up, and you lose credit for something you never had to do to begin with, and then you never do it again. So you'll either learn now or you're gonna learn later, but you'll learn. I've convinced like almost all of you, I think already. Don't simplify unless you're told to. Here, I couldn't stop myself. I mean, it was easy. That being said, I've had students take it to the next level and give me an answer, a final answer of x equals 20 over 2. And I'm like, all right, now you're pushing your luck. I'm telling you, you don't have to simplify algebraically. But 20 over 2, you better put 10. Like, that's not simplifying. That's just doing general arithmetic. Like, simplifying involves algebraic processes. All right, so just be careful about that. If you ever have any doubt, even during a test, did I simplify enough? I might give you a look. The look might be something along the lines of, what do the directions say? They tell you to simplify? You know, that's what the look will say. I won't say that out loud. But it's going to be that idea. Now, if you show me something like 12 pi over 6, I'm going to say, yeah, you probably want to go another step on that one. You know, so, but I'm pretty good about sharing that insight with people during assessments. The only thing you can't ask me to do during an assessment is like the problem. Where did the page? Oh, there it is. It's hidden on me. Like